Okay, last one in this lecture, developable surfaces, and I dare you to say that 10 times fast. Developable surfaces are basically the way that we unfold the Earth. So these are the surfaces, if you imagine that you've taken a piece of paper and stuck it on the side of the Earth or wrapped it around the Earth in some way, traced the land masses and the water and all of that stuff, and then unfolded it into a flat map. So I'll show you a picture here in a second, but these are basically the three simplest platforms by which we do this. These are all created with mathematical expressions, and so there are some more that are much more complicated processes and can't really be entirely replicated by rolling a piece of paper around the globe. But we're going to start with these three basic ones, and then I'll talk to you about some of the other ones. So each one's got pros and cons, and I'll talk about that a little bit as well. So first thing is we have our Earth, and then we have our three basic surfaces. So we have a plane and a cone and a cylinder. And so the plane is literally like you take a sheet of paper and you stick it on the side of the globe, and there you go. The cone is like you curl the paper into a cone shape and make it like a party hat. And then the cylinder is simply wrapping the paper around the globe. So you trace the Earth onto this surface, and then you unfold it, and you get something that looks like this. So I'll show you examples as we go through, but basically the planar ones, right, the flat surface, the plane, will often look sort of like a dartboard because it's used very commonly for polar maps. So you stick it on the North Pole, or you stick it on the South Pole, and so then of course your lines of longitude are radiating away from the center, and your lines of latitude form concentric rings. The cone shape, right, if you imagine the globe, or you can use your head as an example, you make a cone and you stick it on there, and it's going to get kind of stuck in this midsection, so it doesn't make it all the way to the equator. And then you trace the lines of latitude on there. When you unfold it, they're curved like this, right? And then lastly, the cylinder, you're going to draw the stuff on here, and we've talked about this a little bit with the Mercator and unprojected latitude and longitude already. You're basically peeling open the Earth at the poles, and you get graph paper, okay? So we're going to take those three basic types, the plane, the cone, and the cylinder, and then we're going to add to that three aspects or directions in which you stick that surface on the globe, right? So the normal aspect is what we just looked at. We stick the planar projection on the pole, we wrap the cylinder around the equator, we wrap the cone around and stick it on like a party hat. Transverse aspect is you turn it 90 degrees, right? So we've stuck the plane somewhere on the equator, we've wrapped the cylinder around a line of longitude this time instead of the equator, and we've wrapped the cone around in that same process so that it's touching on a line of longitude. And I will tell you, this one is fairly uncommon. You won't see it very often, but it does exist. And then last but not least is oblique, which is basically any other angle that isn't normal or transverse, right? So you stick it on its side, right, at kind of a crazy angle, or you wrap it around kind of diagonally if it's a cone or a cylinder. And so I'll show you a few examples of oblique, but these three on the top, very common. The transverse cylindrical, very common, right? Everything else, less common. But basically you have three shapes, right? Three surfaces, three aspects, and you get this combination of things, okay? Just to make things complicated, we add one more variable, and that's case, right? So you have type, aspect, and case is how you define your projection. And case has to do with basically how many places it's touching the Earth. So in tangent case, for example, with our cylinder here, tangent case, we're touching at the equator. Secant case, and I know it's going to be really hard to see on the screen here, is kind of squished in a little bit, and so the Earth is sort of bulging out in between. So here in this larger one, you can kind of see how this is working, right? So tangent case would just be touching at the equator and kind of running along from there. Secant case, we've sort of snugged it in, right? It's like that pair of pants that doesn't quite fit after months of quarantine. We've snugged it in a little bit, and so what's going to happen then to the distortion in tangent case everything will get peeled away to meet the piece of paper. In secant case, this bit in the middle is going to get squished, right? So we're going to squish it down to meet the paper, and then we're going to peel this away to meet the paper, all right? So that makes a difference because it has to do with where, remember, the whole point to minimizing distortion is to make it somebody else's problem and to push it away from the area that we're mapping. So these three combinations, type, aspect, and case, allow us to do that in certain ways, okay? So I'm going to walk through these a little bit. We'll start with cylindrical projections because they're maybe the easiest to think about. So you got your globe and you've wrapped a piece of paper around it. In tangent case, remember it's touching just at that one spot, right? So in this case, just at the equator. Secant case, I've shrunk it in a little bit and it's going to be touching at two spots, right? So there's extra globe here and then not enough globe here. So we have to squish and stretch. Transverse Mercator, we turn it 90 degrees. So now our point of tangency is along a single line of longitude. And then oblique Mercator is whatever crazy angle you want, right? So why would I use these? Well, notice that the normal cylindrical wraps around the equator. So anytime I'm making a map at the equator, this is a good choice because it doesn't distort, right? So Mercator projection, like I said, we've made a lot of fun of it here. It's really good for certain things, but it doesn't distort as much along the equator as it does in the extreme latitudes. So if I'm just mapping the equator, it's not a bad choice. It's not going to be terribly distorted, right? Transverse Mercator is going to be minimal distortion along that line of longitude, and we're going to talk about that more with coordinates and why that's important. And then oblique Mercator, remember, whatever crazy angle you want. So in this case, if I'm doing North and South America, I would run that line of tangency so that it sort of connects the two, right? I'd probably turn the map so that it's more conventionally oriented north for me, but it's going to minimize distortion around this line. And I'm going to talk a little more about that in a minute, but we'll get through the shapes first. All right, so conic projections, right? We make a party hat, we stick it on the globe, it's touching at one line of latitude, like so. So we're peeling the Earth out and stretching it to meet the paper with a tangent case. In secant case, right, we've snugged it up. It's now touching at two parallels. So we're stretching out here, we're stretching out here, and we're squishing in the middle. Yeah. Okay. And then last but not least, the plane. So this is just a flat sheet of paper. We stuck it on the globe. If we do tangent case, it's only touching at one tiny little point. So that gives you a very small area of no distortion or minimal distortion, right? And then, of course, we're peeling away the globe to meet it everywhere else. So we're distorting as soon as we move away from that point. So if we do secant case, we've sort of jammed that paper on a little bit. And we're going to have a ring of tangency along a line of latitude in this case, because this is normal case. And then squishy in the middle and stretchy on the outside. Okay? Planar also gets a slightly different set of labels. You can certainly use normal, transverse, oblique. That's perfectly fine. But you may also see these terms here in various places. So polar is the same thing as normal because it's sitting on the pole. Equatorial is the same thing as transverse because it's sitting on the equator, and then oblique is still oblique, okay? You don't have to learn those terms. I just want you to be familiar with them because you may read something that says that and you'll be like, wait a minute, I thought it was normal, transverse, and oblique. And it is. It's a mixed bag. The folks in the industry refer to them both ways. Okay, so rule of thumb, cylindrical projections, normal cylinder wraps around the equator, really good for the equator. If I want to get a little bit wider zone around the equator, I'm going to stretch that out a little bit, okay, by doing secant case to give myself two places of tangency. And we're going to do, not today, but in the next chunk of videos, so the early next week batch, we're going to look at that distortion a little bit more specifically. All right, conic, we make a party hat, we stick it on the Earth. Look at that point of tangency running right along the southern United States. So really good for doing wide things like the continental US or Europe. And then we can also spread it out, make it secant case, and have maybe a line of tangency on either side of North America, or, near the top and near the bottom of North America, and get minimized distortion across the continent. The planar type, which is sometimes also called azimuthal, again, good for the poles, right? You stick it right on there and you're good to go. And you could do, like, if I'm just doing tight on the North Pole, I might do tangent case. If I'm going to do a little wider on the North Pole, or maybe do like the Arctic Circle, for example, or all of Antarctica or something like that, I would do secant case and expand that tangency a little bit. Other aspects of this, like transverse, are good for small areas. So like a small island cluster somewhere, maybe you could use a planar projection. There's also one alternate planar that's stereographic that we'll talk about next time as well. So I'm getting ready to do my map, and I need to pick out a projection. How the heck do I decide what I need, right? Remember, the whole goal is to minimize distortion. We want to push it away from the area that we're mapping and make it somebody else's problem. Now, if you're mapping the whole world, obviously you can't push it away. We can't just like transport it to the moon, but we want to make it sort of minimal everywhere. But in this case, we're talking about something smaller than the whole Earth, so a country or a state or a study area or something like that. So I want to get that distortion off my map and into another area. The second thing to think about is that when I'm doing analysis in GIS, every layer has to have the same spatial reference, right? So one of the things you'll do in one of your labs here is going through projecting the layers to get them ready for analysis, okay? So first I have to decide what it's going to be, and then I've got to actually do it. So let's talk about the decision process. And the first thing is, what kind of distortion do I want to avoid? Well, if I need to preserve shape, I'm going to pick an equal area projection, or I'm sorry, a conformal projection. If I need to preserve size, I'm going to pick equal area. If I need to preserve distance, I will do equidistant. And if I need to preserve direction, I will do azimuthal. And remember, the first two are going to be more common than the last two. What part of the globe am I on? That's going to make a difference as well, right? So we just talked about that one. Cylinders, good for the equator. Or if I do it transverse, it's good for long, thin things that run north-south, like, for example, Chile. And then conic projections, really good for wide places, wide states, wide countries, wide continents that are in the mid-latitudes. And then planar is generally the poles, but also some small areas in other places. And then lastly, what's going to make my map look good? Right? How do I do that for the entire extent of the map if I'm doing a larger area? So I need to think about aspect, first of all, which I probably thought about that a little bit anyway, depending on the part of the Earth. But aspect is going to help me refine that surface, whether I run it normally, transverse, or oblique. And then lastly, the case, how many points of tangency do I need to really cover this whole area? Okay, so that's kind of the decision tree that we go through. And that's it for this particular lecture. But in the next lecture, we're going to pick up with this and talk about what the distortion is actually happening, and some other specific things about making sure that you've got the right projection for the job. All right, thanks for listening.